Welcome back to day 2 of the June 2026 Python and Research tutorial series brought to you by the CREST department at the University of California at Santa Cruz. My name is Jamika Marshall, and I am the Python and Research Program Manager. Some of you also know me as the Shadow the Scientist Programs Manager. Thank you all for joining us again today. On screen is today's schedule. Please take a look at it while I go through just a few notes. So yesterday, we explored the fundamentals of Python programming, scientific research, and stellar astrophysics. Today, we'll build on those skills as we dive into Doppler shifts, stellar spectra, galaxy mergers, radial velocities, simulated galaxy disks, and velocity dispersions, all through hands-on activities using real scientific techniques and data. Now, I'd like to thank our mentors and subject matter experts for volunteering their time and expertise. Just as yesterday, they'll be helping lead our notebooks and answer questions throughout the session. As a reminder, we welcome all comments and questions in the chat anytime throughout today's tutorials. Now, for questions that require attention from our mentors and subject matter experts, I will place a red question mark underneath it so that our SMEs and mentors can quickly identify which questions need to be responded to. Now, whether you're feeling confident or still getting comfortable with Python, remember that this is a learning process. Ask questions, experiment, make mistakes, and most importantly, have fun. We're excited to continue this journey with you today. All right, let's get started. I'd like to invite our mentors and subject matter experts to briefly introduce themselves, and starting at the top of my screen, Aparajito.
Yeah. Hi, I'm Jupyter. I work with Raja. I do some research in astronomy. I work with data from nearby galaxies. So, a lot like the galaxy you'll see today, you'll study today for this paper, the paper that you created. And I'm joining you from India. So, hi. Yeah, over to you,
Wonderful.
Jamika.
Thank you, Aparajito. Next, we have Erin Figueroa. Erin, welcome. Quick introduction, please.
Aloha, my name is Aaron. I am a science operations specialist at Gemini Observatory here in beautiful Hilo, Hawaii. And I've been a research astronomer in radio astronomy for 20 years. So,
Wonderful. Thank you so much for joining us, Erin. Next on my screen is Annalise. Annalise, welcome.
Hello, everyone. I am Annelise Jooste. I am from South Africa, Pretoria. I'm actually a PhD student in astronomy. My interests are in variable stars, particularly working in WUMA or contact binary stars, and also a previous participant, or can I say attendee, of this program, and benefited immensely. So I would also like to help tonight a little bit. Thank you so much, Jamika.
It's a pleasure to have you, Annalise. Thank you so much. And last but not least, Sergio Gomez, who I've actually met here at the American Astronomical Society summer meeting here in Pasadena. Sergio, welcome.
Yeah, thank you for the introduction, Jamaica. So, yeah, my name's Sergio. I'm currently a grad student at Cal State LA, so AAS meeting wasn't far from me. And I'm currently in a research group that studies protostars, but before that, I also had some research experience with black hole simulations.
Wonderful. And these are your mentors and subject matter experts for today. So please don't hesitate to put your questions and comments in the chat. So again, we are going to jump right into our section, our astrophysics background on Doppler shift and stellar spectra, and that is with Sergio. All right, Sergio, take it away.
All right, let me just start sharing the screen. All right, can everybody see this?
Yes, we can see your screen and hear you perfectly.
All right, good. So, one of the key things we're touching on is the Doppler effect, which is something that everybody, whether they realize it or not, has had some experience with throughout their lives. And it's just what happens when an object in motion is emitting, in the case of this example, sound, just any sort of wave. And if it's a wave, and oh, I kind of jumped ahead on accident with the slides, but I'll get to it anyway. So when an object in motion is emitting some sort of wave, and when it's approaching you, you hear the pitch change in one way as opposed to when it's moving away from you. So in this example right here, with an ambulance and its siren is going off, a person standing ahead of it, hopefully not in front of it, will hear the ambulance at a higher frequency or a shorter wavelength than a person who's standing behind the ambulance, hearing it go away from them. And so this is something that it happens with any sort of wave, not just sound. This is something that also happens with light and is a very frequently observed and very useful, I guess, phenomenon that we see in the universe. So as I stated, this is something that also happens with light. If, for example, you have a star like the sun, if it's moving away at a certain velocity, then the wavelength of the light that it emits also gets stretched by a certain amount due to its velocity. And if it's going towards, the wave gets squished, becomes higher frequency, again, corresponding to the velocity if it's moving towards you. So that first phenomenon, where it's moving away and the wave gets stretched, becomes lower frequency, is what's called redshift in the case of light. And there's various different ways that it can happen within the universe. As mentioned, there was the whole relative motion between two objects. Here we see, in this GIF, we see two galaxies. They're getting closer, but of course with the redshift, it would be in the case of, for example, a galaxy moving away from us. It's something that you'll see is a reason a lot of James Webb images are quite red. If you see an example, for example, something that one image of a very distant galaxy from way early on in the universe, which then leads into this second type of redshift, the expansion of space between two objects. Because one thing that we've discovered throughout the last century is that as the universe expands, it's because of space itself expanding. And so two objects very far apart will only get further and further apart because of that expansion. And so the light that each one receives from the other also gets stretched out by that expansion. And then the third cause of any sort of redshift is from gravitational effects. For example, you may have seen an image of a galaxy where it's been gravitationally lensed. The force of gravity for any massive object causes different light to get affected in different ways, and one of those ways can be gravitational redshift. It's something that I had to account for when doing some analysis on simulation data. When I mentioned I was doing research on black hole simulation. So now this redshift is, like I mentioned before, a very useful thing to quantify for astronomers and astrophysicists, because as you can see, it helps to measure the distance of deep space objects. For example, something can be emitting light from billions upon billions of light years away. And the redshift that we see tells us how much further out it might be, because the light might be a certain age, but that doesn't tell us where it is and where it's moving currently. And building on that, redshift itself helps determine the relative age of galaxies. And one of the most, I guess, more recently than ever, we're also being able to use redshift to find exoplanets. This is something I think that might be touched on when it comes to the radial velocity Python tutorial. I haven't had a look at it yet personally, but I know for a fact that when it comes to detecting exoplanets around stars, the star is tugging on the planet, and the planet is also tugging a little bit on the star. And so when looking at the system, the star, even though the planet might be tiny relative to the star itself will still experience some sort of motion relative to a shared center point that they have. And so the light will be slightly red shifted or blue shifted depending on where it is, where the star is in that relative orbit. And so that tells us, oh, there's something else there, something we can't see. That must be an exoplanet. So when it comes to that aforementioned redshift, it also causes the wavelengths of light. It causes the wavelengths of light that's emitted to shift even in the visible range. And so that shift is something that we can measure by comparing it to a stationary result gained from, for example, a lab. From a lab frame, for example, you'll see this wavelength rest is here, but then you might detect something that looks just like the stationary, but just shifted one way or another. And so that's what we see here with the wavelength nu. And in terms of, again, maybe you skimmed like a paper or seen like a magazine or something, you've seen the shifted spectrum of a star before, these sorts of plots right here. So once again, we have an example of showing where the wavelength and the whole spectrum would be for the star at rest relative to us. And then the blue curve shows where the star is as a consequence of its motion. And see that it's all been shifted in one direction. And all this can be determined. And we were able to learn so much about it because through the use of this Doppler shift formula, wherein v is the velocity of the star, in which, well, negative would be moving towards and positive moving away, divided by the speed of light, plus 1, and then that whole quantity multiplied by the rest wavelength. And you can similarly convert this formula into its frequency form, which is something I know very often also done in astrophysics. It's something I had to do recently, or it's a form of the formula I have to work with recently in terms of protostars. Since I'm working with a source that's moving away from us, it's all of its emissions in various different molecules and atoms have been redshifted. So I'm sure somebody in the chat, one of the other experts might send the frequency version of this, but it otherwise has a very similar structure. And yeah, that's the end of that slide. Thank you.
Thank you so much, Sergio. All right, so we are ready for Notebook 4. Now, before we begin, again, we welcome your comments and questions in the chat. I am recording the chat so that I can send the transcript to everyone afterwards. This way, all the questions and comments, explanations that our mentors and subject matter experts share in the chat is recorded for everyone to use as you go back and work through these notebooks on your own. Okay, Notebook 4 is going to be led by Aparajito. We are ready for you. Thank you, Aparajito.
Okay. I think you can see my Chrome window.
Yes, we can see your Chrome window and we can hear you brilliantly.
Perfect. Let's start by turning on line numbers. Okay, so quick recap of yesterday's 3 notebooks. We learned the basics of Python, the basic data types and the basic operations we can do with them. We learned a little bit about NumPy, and Matplotlib. So how to work with large data sets of numbers and how to plot them. And we saw a little application of those skills. We saw how the data visualization, that plotting can help us do things, allows us to do things that you couldn't do by, just staring at the numbers. So now we are getting into the more, say, physics thing. Okay, so Sergio just gave you an excellent introduction to Doppler shift. Now let's apply that knowledge to something in astronomy. Some data that you already have. Inside this folder called data, you will find 3 files with numbers for names, right? A bunch of numbers underscore spec.txt. Okay, so what they contain is basically a bunch of wavelength values and a bunch of flux values. Okay, so they give what is basically a spectrum. We just learned what a spectrum is. So this stores the spectral values for 3 different stars. These are real stars in the Andromeda Galaxy. Okay, they were observed by real telescopes. They were observed by astronomers, and we are storing this data in text files, which is unconventional. Usually we use something called a FITS file, but we're making things easy for you. We're storing them in we're storing them in text files. You can just open them up, look inside. What do they look like? Loading. See, there are 2 columns, one for the wavelengths and one for the flux. Okay, so one is the x-axis, the other one is the y-axis. And you'll also see 3 files here: ms, agb, and rgb underscore tmpl. So these files look very, very similar on the inside, but the tmpl means that they're templates. Okay, so these are not real observed spectrum. Rather, this is kind of an amalgamation, a model based on a bunch of spectra of these 3 types of stars that we have observed. Okay, this is like the ideal case. Okay, this is a yardstick that will compare the real data against. So why are we comparing some real data against these templates? What is the point? Let's see. Okay, so we'll start by loading NumPy and Matplotlib as usual, and then we are creating a function, a user-defined function called shift to moving. Okay, this is a function to shift a wavelength using Doppler equation. And as you can see, so far it doesn't do anything really. You have to complete this function. We have to write a function that takes a spectrum and shifts it, Doppler shifts it according to the velocity provided. Okay, so does anybody have any idea what formula we should use? We already know the formula. What is it?
Let's see if we
It's
get
rest lambda.
Yes.
It's rest lambda times.
Sophia said the ones that Sergio showed you.
Right. Okay.
And Gavin has given us the equation there.
1 plus v over c. Yeah. So by the way, the lambda goes over the whole thing. So let's just do that. I'm going to times. Sorry. 1 plus v over c. Okay. This is what it looks like. Okay. But you can see that I used c here. So we have to define c. C is the speed of light. And I'm just going to copy that value from somewhere else. Save some time, but you can just, Google this value. And this is the speed of light in kilometers per second. Okay. Now, we have to find the function. What does it take as argument? It takes a rest lambda and like a rest frame array of wavelengths, and it takes a velocity, right? It uses specified velocity. And then it just uses the Doppler formula using the velocity of light provided here, which is constant, as we know. And it uses this Doppler formula to just shift it to a new array of wavelengths. Okay, so now we're going to use this formula for something. We have a rest frame, H alpha wavelength. Okay, so H alpha is a very famous emission line produced by hydrogen. If you heat up hydrogen, one of the lines, one of the specific wavelengths that it gives out is this 6563. This is in angstroms, okay? And what we're going to do is shift it by a couple of values and see how it goes. So let's try that. Going to print. By the way, you can just hit tab to autocomplete if you already have a function or a variable defined here. And this rest H alpha. And I'm going to do a velocity of, say, 100. Okay. First, let's just do Z and see if it gives us, it returns the exact same value, right? And it does, okay? So it works for the rest rate. Now let's put in 100 kilometers per second. Okay, 6565. Okay, you can see that it is a high end, right? So it has been redshifted. Okay, because the velocity is positive, so the thing is moving away from us, right? Let's try the values suggested here. I do 200 kilometers per second. You can see that the change is even bigger. And once again, it's high, the wavelength is higher than the rest frame wavelength, which means it's shifting towards the red side of the spectrum. Okay, so this is a red shift. If I do negative 200, what does that mean? You can see that it is lower. Now this value is lower than the rest frame wavelength, and that means it is blue shift. Negative velocity means that the target is moving towards us. Okay, that's what we are simulating. Okay, now, what does this say? Now, on to our 3 stars for today's activity. The first step is to pick a science star. Science star is one of the 3 stars, the 3 real observed stars that we just saw from the 3 files. And a template star, and read in the files. Fill in the star name. We saw the names. There are a bunch of numbers. That's how stars are recorded in catalogs. A bunch of letters and a bunch of numbers. And then we mention one of the types. So MS, RGB, or HB. So we are going to plot some real spectra against a template spectrum and see which template matches it the best. But we have to do some adjustments for the Doppler shift to find the exact correct template. Okay, so I'm going to pick 491422. Okay. Like this one. And I'm going to start with MS. Okay. I'm going to assume this is a main sequence star. And I'm going to load in the size file and the template file. Okay. And as you can see, it loads in the data and splits the two columns into lambda, which is the usual Greek symbol to denote wavelength, and flux. So we have an x-axis and a y-axis for the two kinds of data, the real data and the template. Okay, so let's run this cell and see what it gives us. Okay, it doesn't show me anything. So if it adds something called plt.show, let's see if that works. You might have to do the same. Sometimes the plot doesn't appear. I suggested this in chat yesterday, but if your plot doesn't appear, just add this line plt.show. Backends are complicated. It depends on your system. It depends on the browser. It depends on the version of Anaconda, a bunch of different things. Anyway, so we have the science data in red, and we have the template in black. So does this look like a good match? Anyway, in the guess, let's just say yes or no in chat. Does this look like a good match? Do the black line, does the black line and the red line overlap neatly?
Yeah, we have some responses coming in. No, from Jeff. Jeff sent that directly to me, but he says no, and I'll copy it there.
I also got a no directly. Okay, so it doesn't look that good. I agree. It doesn't look that good. So let's try something else. Let's try AGB. Okay. And remember, the templates are like the ideal model spectra of stars of these types. It won't be a perfect match, but it should be a good match. So this is AGB. The red line, it might look different now because the scale has been adjusted automatically, but I assure you it is the exact same spectrum in red, but the template in black has changed. Is this a good match? I'm still quite not satisfied. It's a little bit better, but it's not that good. So finally, let's try RGB. Okay, now we're on to something. This looks really good, doesn't it? This big feature matches here. This big feature too. You can see that the slope here matches roughly, right? And then it goes down and up again. It's pretty good, right? Again, remember that it won't ever be a perfect match because one is a template, an ideal spectrum. The other one, this is proof that the real world is just messy. And we scientists are trying to categorize things to the best of our abilities, but there are always, confounding variables. There are little deviations from the ideal. But this is a very real science case, right? Now, there's still a little bit of deviation, like I said, and maybe we can get rid of some of the deviation because you can see that vguess, the guess velocity that I provided to shift the template here, right? Sure, the template is what we are. Yeah, shift the template here is 0. So I'm not shifting the template at all. But the real star, remember, is from a neighboring galaxy. And the galaxy is moving relative to our galaxy, as you'll find out in a later section, maybe later astronomy section. So this star has some motion, some significant motion relative to the Earth's reference frame or the Sun's reference frame. Okay, so you have to account for that. Thus, we guess it cannot be seen. So first of all, let's zoom in into a little section. It says 7,000 to 7,200. That's the limit it suggests. So that's the limit we're going to use. Going to insert it here. Oops. Okay. Now, we've zoomed in to a small section of the spectrum, right? Now we can match this template more precisely. This is much better than looking at this whole thing zoomed out. You can look at the minutiae, right? The little features. We can match these little peaks and valleys. Let's try the positive velocity. Note that the black line is slightly to the right of the red line. Okay? It's really obvious here. See? Where the red line goes down here and the black line goes down here. The black line is shifted to the right. Okay? It's also noticeable here, right? So let's try doing a positive velocity. Maybe that's the solution. Do the two lines come closer together? I'm going to do 200. Okay? This doesn't look good. The lines are further apart. Okay? So maybe I should do negative values, right? That should move it in the opposite direction, right? Okay, much better. Maybe it can go a little bit more. Let's say it's 250. Okay, this is good. I think it's moving too much to the left here because you have to look at the whole section, all right? Maybe something like 225. Yeah, I think this is okay. This is a good balance, right? The left side more or less matches, and the right side more or less matches. Okay. You can comment out this line. I'll look at the whole thing again. Oh, it looks slightly better, doesn't it? All right. Let's zoom in again. Okay. Good. So we have just found the velocity of the star, roughly. There are more precise ways to do this. There are automated ways to do this. Look up cross correlation if you're interested. And as you can see, there are two more stars here, but we're not going to go through all of those to save time. But you should do this in your own time. I'm leaving this as an exercise to you. And we're going to move on to the next section. Okay, so we just saw how to measure the velocity of one star. We can do this automated, but the principle is basically the same, right? Whether it's manual, automated, or a mix of manual and automated, the principle is that you have a real spectrum and you pick the right template to fit to it, and you Doppler shift it until the template fits really well. until you get an optimal fit, an optimal match, an overlap. And you will have a guess velocity. Should we count how much time do I have?
22 minutes.
Okay, great. So you can see that we are reading in the data from KKHST data. This is, I believe, the same file that you used yesterday for Notebook 3, right? This, if you remember, is a huge catalog of stars. And it has RA and dec value. RA and dec is basically like the latitude and longitude on the sky, as you learned. Chi and eta are also coordinates. These are coordinates in a more specific galactic frame, or I shouldn't say galactic frame, because that means a different, but it's a frame defined with respect to the M31 galaxy, okay? And we have the brightness of these stars. We have the magnitude of these stars in two different filters, and we also have the velocity data and the error in measuring the velocity data. Because remember, in science, we have to report error every step through, right? Error calculation is very important in writing papers, presenting results. Is a whole, it is a whole branch of basically mathematics in and of itself. So we are loading all of that data from the huge catalog file. And you can see that we have something called degree to KPC. And KPC just stands for kiloparsecs. And there's a number, and what we're doing is multiplying the chi and eta by this factor, right? So what this does is basically takes a distance measured in degrees on the sky. Because remember, it's like latitude and longitude. It's just like, measuring distances on Earth. You can measure it on a globe using degrees, using the latitude and longitude. And then you can convert it to actual distance between the two, right? Or rather, apparent distance between the two, because we can't actually measure in 3D here. So the actual or rather apparent distance in kiloparsecs is simply a multiplication away. That's what it happens for large distances. It's just small angle approximation of the tangent function. It's basic trigonometry. Anyway, so you're taking these values in degrees and we're converting them to kiloparsecs. Let's run this cell. Why doesn't my pointer work? Oh. Okay. So now we're going to plot all of the stars into a map. Okay. Once again, I have to add plv.show for my system. You might also have to do that. And you can see that there's a lot of points, a whole lot of points. Okay. Now, what have we done here? We've just done a scatter plot. And we've just used the chi and eta coordinates. Okay. You can see that they're in kiloparsecs. So we can see that the apparent distance along the x and the y axis. You can see that we also have the radial velocity as a color map. So this is basically three-dimensional data represented in 2 dimensions. you have an x coordinate and a y coordinate, and a third value in the form of the color, right? In the form of the color map. So the color map represents the velocity. You can see that this is roughly the zero velocity, and all of this is basically a section of M31. So you can see that this is not the whole disk of a galaxy. You might have seen pictures of galaxies before. You must have seen pictures of galaxies before. They look like ellipses, right? Spiral galaxies, and M31 is a spiral galaxy. So it's looking like ellipse. This is like some portions cut out of the ellipse. Because the galaxy is huge, for this survey, we just picked out stars from certain sections, okay? So this is a cutout from the whole galactic disk. Now, okay, now we're going to do something which is change the color, okay? As you can see, this color bar includes negative velocities and positive velocities, okay? And also roughly zero velocities, which means that this was adjusted, right? The velocities were adjusted so that we are looking at it where we are relatively stationary to the center of M30, okay? But since this is a spiral galaxy, the whole thing is rotating, okay? Which means some parts of the galaxy are moving towards us and some parts of the galaxy are moving away from us, okay? So if this is the galactic disk, right? You're looking at it tilted, okay? You're looking at it tilted, and it is spin, right? The center is what we are relatively stationary. But if it is spinning, see the hand at the top is moving towards you, and my hand at the bottom is moving away from you, okay? Now, let's try to represent that with a color. A color map that actually reflects this movement. What do we know about things that move away? They are redshift, right? And things that are moving towards us are blue shift, right? So let's represent that. Maybe there's a color map that can do that. What I'm going to do is look at matplotlib cheat sheet. Okay, so I have the link somewhere. In a different browser. Okay. Let's go directly to the page. So I'm once again putting this link in the chat. I have put this link in the chat yesterday. This is a very useful resource, an official matplotlib resource. It should give you an overview of, oh, sorry, I sent it as a direct message to one of you.
I added it into the chat per detail.
Thank you, Jamika. Thank you so much. Now, we're going to look at the different color maps. You can see that there's a section of color maps. None of these are that good. One of these might work. It's called Cool War, but maybe there's something else. See, there's a bunch of color maps here. So can I use one of these? I like this one, PWR. This might be it. Let's do this, okay? PWR. I'm going to change the color map from Veritas to PWR. Okay. Does this look right? This looks right. Yes. Positive velocities.
Aparajito, you have to put
Yes.
the positive and negative values to be the same for your Vmin and Vmax so that the white will be centered on 0.
Right.
I
Thank
do that
you.
all the time.
Yes. Thank you. So this looks more or less right in terms of the color, but as Maddie pointed out, I think that was Maddie. So we have to balance the colors because as you can see, this whole section looks red. Okay, not only are the positive values red, some of the negative values are also red here. So something needs to be fixed. And what needs to be fixed here is the positive and the negative limits. Okay. Ooh. Let's see what that does. Oh, this does. Any ideas, mentors? I forgot how to fix this.
I have a vague memory of this being something to do with the fact that what we're seeing is one of the arms of Andromeda that's predominantly moving towards us. And so the fact that it is almost entirely blue is perhaps not inappropriate.
All right. Okay. Yes, I remember. Thank you. So, if I put an equal limit, you can see that the whole thing is blue. Okay. So, this is basically not adjusted velocities anymore. This is not an adjusted color map anymore. You can see that all the velocities here are in the blue. All right, all the velocities are here in the blue because we have adjusted the color map, the color bar, such that 0 is at roughly a white color, and all the positive velocities are red, and all the negative velocities are blue. Okay, so the perspective that we had so far of adjusting to roughly, Andromeda's reference frame is gone. Now we're looking at it from our normal reference frame. Now we're looking at it from a heliocentric or the sun's reference frame. And as you can see, the whole thing is blue shifted. These are the real velocities, remember. The color map was being adjusted, the real velocities are never being changed. And if we adjust the color map so that all negative velocities read as blue, you can see that the whole thing is blue shifted because the Andromeda Galaxy as a whole is moving towards us. Okay? So, go back to the normalized color map. We're going to look at it in a roughly adjusted color map again. And you can see that one part is floating away from us, while a little bit of the part that's floating towards us is visible here. I think the center is somewhere roughly here, as you can see at 0, 0. Remember, these are relative coordinates. So that's where roughly the center of Andromeda is. You can see that's where the red and the blue mix. All right. Did I get anything wrong? I think this is okay. Yeah, that's it. That's it for this notebook. Now, what does this mean? What does this whole galaxy evolution mean? I think that's part of the next section, or maybe that's what does an exercise. Jupyter.
Thank you so much, Aparajito. And also, you heard there chiming in with Aparajito, one of our subject matter experts and mentors, actually, from many previous Python tutorials, Madeline Broom. Thank you so much. Yes, that is fantastic. Now, I am looking in our participant list to see if our mentor for our next section is here, and I don't see Lordrick. And this was to cover the galaxy mergers section. I'd like to welcome Aparajito or Sergio or Madeline or Annalise to maybe give us a quick look at the galaxy merger slides, talk about those. Would either of you be able to do that for us? And if not, we can come back to it when Lordrick joins us, because we are a bit ahead of time. Aparajito, I see you. Yes?
Oh, no, I was hoping to rest the
No
voice a little
worries.
bit. Yeah.
Absolutely.
I can potentially take a crack at it if all the other mentors are willing to help me, because I haven't taught this one in a couple of years.
Absolutely. Yes, I am sure that they are willing to help you. Aparajito is nodding. Sergio is nodding also as well. Okay, thank you so much, Madeline. Take it away.
Well, let's actually take this opportunity to maybe have a 2-minute break because I need to move to a place where I can talk loudly.
Okay, let's take a 4-minute break, in fact. Let's do that. Thank you so much, Aparajito, Sergio, and Madeline. So while we're taking this break, I did get a few questions about the link to the recording of yesterday's tutorial. I did send that out in an email yesterday along with the chat transcript. So please check your email for it. I did also put it in the chat earlier. If you need me to post that link again, please let me know. It's no problem. And yes, I will, of course, share the recording of today's tutorial session with everyone who is registered. Thank you so much. Yes, thank you, Parjito, for that reminder in the chat. If you have any questions, please go ahead and post them in the chat, and also any comments as well, too. If you're just joining us, we are taking a bit of an unscripted break here. We have one of our subject matter experts, Madeline Broom, is going to jump in for this next section on galaxy mergers. So we have another 2 minutes for our break.
Turns out Lorgic was having some trouble with the Zoom link, but here he is now, and so he'll be able to lead us in a second through Notebook 5.
Brilliant. Thank you so much for that update, Madeline. And oh no, Lordrick, I'm sorry you were having trouble. I don't see Lordrick, Madeline.
I was just on the phone with him, and he was able
I'm
to receive
here.
the link in the email, and so he should be here.
I hear you. Are you under Lordrick?
I should hope so. Unless something changed.
You're showing up as me, Lordrick.
Yeah.
Oh, am I? Oh
Yeah.
my gosh!
That's
Because I used your link. I used your link.
okay. I thought it was just me. Okay, so Lordrick, will you rename yourself, please?
Okay. I'm only now realizing that I'm showing up as Maddie. Okay, let me see if I can rename this. God, I've never even done that. Let me see. Video settings, is it?
Oh, I can rename you on my end. No worries. I got
Okay,
you.
thank
Let
you.
me do it right
Yeah.
now.
This is not Madeline. This is Lodrick. All right.
Very
Thank
cool.
you. And thank you, Madeline.
Thank you, Madeline.
No worries.
Oh my goodness. And
Mhm.
welcome back, Lordrick. For
Oh, wow.
those of you who were not with us yesterday, Lordrick was one of our mentors. Lordrick, could you give our audience a very quick intro before we jump into the Galaxy Merger section?
Right. Yes. So I'm Lodrick Kahinga. I'm a PhD student. I'm a third year at UC Santa Cruz. I work on fast radio bursts. I'm going to try and share my screen. I had my website up yesterday. Let me see if I can still do that today. Oh dear. So many things going on. Okay. Uh, and the website is no longer. Oh, there it is. Yeah. I'm a PhD student at UC Santa Cruz. I work on fast radio bursts. I'm originally from Tanzania. I've been coding in Python for more than 10 years now. I guess that's all I'm gonna say. And my website is here. I'm gonna put it in the chat if you wanna learn more about my research or want to talk to me about FREs, I'm happy to do so. And I
Thank you
don't
for
know where
that
the chat
link.
is anymore. Where's the chat?
Oh,
Right, there it is.
it's probably hidden behind the screen. Yeah, there you
Yeah.
go.
I hope the name doesn't appear as Maddie.
Nope.
Okay, good. Good.
Got
Yeah. Cool. Okay. Let's get into it. Let's get me fine. So I have another kind of, oh, at least I saw this yesterday and I tried to prep for it. Oh, that's not the presentation we want. Uh, Sorry. Everything's a mess because I couldn't find the thing.
No
Let
worries. Thank you so much for being with us.
uh,
And I will say, you all, that you, if you're, most of you are SIP students, science internship students, who will be joining us right here well, actually, on the UC Santa Cruz campus, hopefully on Sunday. So I look forward to meeting all of you in person on Sunday, as I will be there. And as Lordrick and Madeline didn't say, but they are both at UC Santa Cruz PhD students. So it could be possible that you would be able to potentially meet them. Some of our
yes,
superstars. Yeah. And
I
actually,
would.
Lordrick, I haven't met you in person myself. So I'm looking
Oh,
forward to meeting you next week.
oh wow, that would be nice. Yeah.
That would
Yeah.
be.
And thank you for filling up the time as I was scrambling for those slides. One more thing that I need. And so I found out that the slides we have on Google Slides don't actually have the videos embedded in them, or I don't know how to play them.
No, that's not you. It does require PowerPoint, which doesn't really work well on my screen, but no worries.
Okay, so I prepped for that in that I put something at the bottom here.
Oh, we
Okay,
appreciate you, Lordrick.
so yeah, this is the cool. Ooh, ads. I'm sorry. YouTube ads. I don't have YouTube Premium. Okay. This is the really cool. We're going to talk about measures and galaxies merging, but first, just to start off, we want to look at the Milky Way, our very own galaxy. And this is one of those cool videos that people have taken, basically just recording the night sky. And let me pause it here. What you kind of see it here, and you could see it with your own eyes when you're in places where you have very dark skies, is indeed the stars on our very own Milky Way. I mean, most all the stars are on the Milky Way, but these stars are exactly on the what do we call on this spiral itself, on the galaxy itself at the disk. And so what you're seeing here, this is kind of a sped up video through the course of a night. And it's essentially as it appears as if it's moving, but that's just a result of our own planet rotating. So the link for this video, it's really cool. I loved it, like when I saw it yesterday. Is in the schedule, but I don't think that's shared. Could you put it in the chat maybe?
I'm sorry, repeat that again.
The link for this particular video.
Yes, I sure will put it in the chat. Thank you for that reminder,
Yes.
Lordrick. I'll do it right now.
Yes, and so back to our cool slides. And so this is the Milky Way. This is the galaxy we live in. Maybe you've seen this image before. By the way, this is an artist rendition of what the Milky Way should look like. We have not had a probe that has gone this far away to kind of get this vantage point and take a picture of the Milky Way. And even if we did, that picture would take a few 100,000 years to, if you're sending it at the speed of light. Don't forget about the object, which is moving much slower. So to get this picture is actually would be a real feat. So maybe a few billion years from now, people will have this picture if people are still around at that point. But this is the artist rendition of the Milky Way. And what is cool to see is that the Milky Way is indeed a spiral galaxy. Why do we call it a spiral galaxy? Because it has this spiral shape, and I hope it was labeled where we are in the Milky Way is this region. And so what you were seeing in that video, where is that video? Here. This little kind of splash of stars here is actually one of these arms. Let me go back. Sorry, I'm going back and forth. If it's a little confusing, I'm happy to kind of elaborate more. What we're seeing is one of these spiral arms. And so something cool. Okay, and another thing is that we're about a quarter of 100,000 light years away from the center of the Milky Way, and I believe there should be a black hole somewhere in the middle. And people have now taken a picture of it with the Very Large Telescope, which is very cool. And so something about galaxies is that they actually do rotate. And so by rotating, I mean that the stars within the galaxies are rotating around the common center. And so in the case of the Milky Way and most galaxies, actually, you'll find that most of the galaxies, they're kind of rotating at the middle. They'll have slightly higher speeds, and then it will be much slower in the outside. Actually, not as slow as we would expect, which is kind of the science that Vera Rubin did in the late 1970s. But I digress. I don't want to get into that right now. But it's very cool that all galaxies have this, or at least all spiral galaxies have this kind of rotational motion, and they're moving within each other, which is kind of the main goal of this kind of presentation. Is we know the galaxies are rotating, and we're going to see in the next notebook how we can kind of simulate that rotation and measure it. And then in the case of the Andromeda Galaxy, which we are interested in, before I even get to that, I also prepared another video link, which was also supposed to be part of that presentation. I think this is the one. Yeah. This is another cool video that I found. I think it's also on YouTube, where it shows the rotation of galaxies. And interestingly, you're seeing two different images here. One of them is rotating much faster, and one of them is rotating much slower. But before even you think of that, the thing I want you to notice is that this galaxy, or both galaxies, are rotating much faster in the middle than they are in the outer part of the galaxy. Now, why are these galaxies rotating at different speeds? I'll tell you one thing about them. They're at different redshifts. That is to say, one of them is much farther away than the other. And I will leave this as a homework to all the attendees, that kind of try to learn about why the higher redshift galaxy is rotating faster than the one that's at the lower redshift. So the one that's nearby is not rotating quite as fast. Okay, cool. Let's go back to our other presentation. So as I was mentioning, that's all about the rotation. And so the way one would actually kind of measure this slash plot this is this is the Andromeda Galaxy, also known as M31. I think you've probably had that over the course of these presentations. And so you have kind of your radio velocities that with respect to us, as we observe it in the Milky Way, you can see kind of, I think, these negative values over here. This part is moving towards us, and then these purple values with the... Oh, wait, I'm very confused now. They're all negative. Yeah, I think, but let me try to remember. Maddie, are you there? Oh, is Maddie gone?
No, Maddie's here.
Yeah.
Oh, and we also have Sergio, who can also assist and answer questions, as well as Aaron Figura and Annalise.
Yes, I was expecting this color bar to be positive and negative, but maybe I'm forgetting exactly the velocity spin plotting here. If you could help me out with that.
Let me see if she's here. Okay. Madeline. Yes.
Sorry, Roger, can you repeat the question, please?
Oh, I was expecting this to show the velocity, the rotation of the M31 galaxy. Yeah.
Right. So that depends on how the color bar is, or rather color map is calibrated, I guess. How we set the limits of the color map. And it looks like, you know, they did not account for that rotation here. But we covered that in the previous notebook. We tried the different limits. What happens when we take a velocity that's relatively rest frame to the center of M31 and velocity limits that cover the whole scale and the whole thing looks blue shifted. So we covered this.
Cool.
So,
thank you very much.
to connect for the viewers, it's logic is just talking about what we talked about in the final cell of that last notebook. How you pick the color bar, how you pick the color map, will show you, will determine how the velocities are displayed. If you pick a frame of reference with respect to the sun, like a heliocentric velocity, which you can see here in this map, all of it will be negative. But if you pick a velocity that's stationary with respect to the center of the galaxy, like we saw with negative 100 and plus, sorry, negative 700 and plus 100, you will see the rotation. You will see a redshifted portion and a shifted portion. Yeah, back to you, Lucas.
Cool. Yeah. So I guess kind of because I didn't want to lie, kind of. So from this image, what I'm looking at is A, the galaxy is moving towards us because Andromeda is going to collide with us. But B, because it's rotating, that means some parts of it are moving towards us much faster than other parts of it. So I would say this part is moving towards us, the bottom right purple, and the upper left yellowish part is moving away from us, and that's how it's rotating. Is that correct, Apurjit?
Yeah, that's correct.
Cool. Yeah, I just didn't want to kind of just assert statements which would be incorrect. So thank you very much. Yeah. So A, two things you want to notice here. The Andromeda Galaxy is indeed rotating. B, it is moving towards us. And moving towards us means it's going to collide with us, which is going to be interesting. Now, there are supposed to be simulations of galaxy collision videos here, which are pretty cool, but I couldn't find the link of a good galaxy simulation video. I don't know, from the last presentations, please, if someone could share that link and maybe people could talk about it later.
Yeah, certainly will. I'll look for some.
All right, cool. Thank you very much. And sorry for kind of the disjointed presentation there. But hopefully things are going to go smoother when we get into the notebook. And so I was kind of having fun with the notebook earlier today. I'm gonna clear all cells. Let's go to kernel, restart, and clear output of all cells. Great. Okay, so in this particular notebook, we're gonna simulate a fake Andromeda galaxy. And so we're importing a bunch of things. We saw this from yesterday. We have matplotlib for our plotting. We have the matplotlib inline command here to kind of help with plotting things on Jupyter Notebooks. We have the NumPy one, and then we have this from fake disk, import fake disk. Now, this is not a standard library. This code is kind of just written special for this particular kind of science, and it's not a standard library you can just import it from anywhere. We're actually importing this from a Python file, which usually is named with .py. And so if you go at the top of your program here and you go into programs, you will see this fake disk.py file where we have this class class fake disk. Now, if the word class also doesn't make sense to you, that's because I think we haven't touched enough on Python object-oriented programming. But don't worry about it. Basically, we're making an object. An object is basically anything. Anything can be an object in Python, a float, an array, or anything. And we want to define some common functions and common variables inside it. This is usually when you might have a lot of these objects. And so you always want to perform some normal functions or have some defined things inside a particular object. And so we define this function, which is kind of every object or every object in Python programming have this function called init. And don't worry about it if you don't understand it right now, but basically just know we're kind of defining the starting point for each one and every one of these objects. And so it has kind of this variable known as inclination. And so this object is meant to store fake disk galaxies. And so, of course, they will have an inclination. An inclination is exactly, are they edge-on or are they face-on galaxies towards us? And then we have a position angle. We'll kind of understand this better when we see the plots. But a position angle is basically how is it oriented if you have kind of a defined north, south, east, west coordinates on the sky. And then it will have some rotation speed. Number of points here, each point is basically just representing a star. And the shape, kind of at the moment, we only have one shape known as constant. We will kind of, for the rest of these values, we will kind of keep them constant as is. Scale factor just defines in kiloparsecs what's the radius of your disk. And then the dispersion, I will talk about later. But essentially this kind of describes if you have one star here, how on average in all its neighbors within some defined radius, what's the velocity of each of the moving stars. And so whenever we start this fake disk object, it will have dispersion defined that way. It will have the inclination value, which you'll put here, which is converted here into radians because it was given in degrees. Let me see. No. Oh yes, it's given in degrees, and so here you're converting it into radians. So we do the same for position angle and rotation velocities and all those things. So you can kind of look at this function and see how all these cool things work out, but they're not super important for the thing that we're going to be looking at today. But just know that we'll be using that to make our fake galaxies. And so, as usual, we're going to do some visualizations. And so we have this function to do our visualization, which is very similar to the one that we had yesterday. The difference is, for the one we were using yesterday, we were using PLT as is. I think I can pull that up quickly just to compare. Here we had a function called initialize plot. You can see we were using PLT directly from pyplot. This is good, but if you want more functionality, we use this axis. Okay, plot.axis gives you a little bit more fluidity, but a lot of the syntax is very similar. And so this just makes our kind of our canvas where we draw, and then here we are labeling our axis. I don't know what the plural for axis is. Is it axi? I don't know. My English is not my first language, so bear with me. And then we set a title. For this case, remember we talked about this psi and eta values yesterday from any of the tables. Let me pull up some of those tables here. Here we have a psi and eta value. These are positions with respect to the center of your galaxy. In this case, we're talking about M31. So that's what we are using here. Where is it? That's what we're using here on our x-axis and on our y-axis. And we're setting the x limits the same way we do. And then if we want to kind of zoom in, we'll just set this cutout parameter here to true, and it will help us kind of, this is a quick zoom in towards the center of the galaxy. And then it will do the plotting using a scatter plot. We are plotting X versus Z. This is Z is just a name, the variable Z, but you can kind of think of it as the Y-axis. And then you will have a color bar similar to what you had in your previous notebooks. And you will kind of define this quantity here will be the quantity kind of color to color those your scatter points, and then you can set an I think there's no edge colors and all these other points, and then here we're just showing the color bar. For kind of the Python people, you can kind of notice how we do color bars here. First, you let your axis, this is the good thing about using axis instead of just PLT directly. You can just let this axis object, once again, object, as in Python programming object, into this variable, and then pass that object inside your color bar option. So this is just what we're gonna be using to plot. And so let's go. Okay. We are defining the scale factor. So we want our galaxy to have a radius of about 20 kiloparsecs. And we are describing the dispersion, how the stars will be a little bit different in terms of their velocity. And then we are defining some inclination. This is the inclination of the M31 galaxy, about 73 degrees. We'll change some of these values to kind of see how they would change our galaxy. And so we are defining some rotation speed, and then we are defining the number of stars. Here I just started with 50,000 because my computer is very strong, but let's just do 10,000 for now. And so let's run it. I think I forgot to run this one as well. Let's run it. So these are our defined values. And so we have initiated, and this is the terminology people use in object programming. We have initialized that object, and we stored it in this variable sim to indicate that this is our simulated fake galaxy. And so we've simulated our fake galaxies with these particular parameters. Let's see. Let's set the plotting now. Remember, Vmin and Vmax here are just gonna define the Vmin and Vmax inside our scatter, inside our color bar almost, to define those points. And so I lost the thing for a little bit there. All right. And so we define just Vmax to be the maximum velocity of each stars to be just about 30% more than the rotation velocity that we started with, which was about 200 kilometers per second. And then we use that function show map now to show our galaxy. So basically this function, it just takes in that sim object, which we have defined here. It's an entire fake disk. And then it takes in this case, what we want to plot in the color bar is the Vy radial velocity, which we have used this label here, and then the Vmin and Vmax, as I talked about before. And so when you're looking at that by yourself, you can kind of compare to see exactly what parameters we are passing through, or what arguments we are passing through this function. And so without further ado, let's plot the fake galaxy. There we go. That is good. That looks good. Now, I'm going to stop here and ask the question I forgot to ask. Actually, two questions. One, how much time do I have?
You have 30 minutes.
I have 30 minutes. That's great. I think I won't need as much. Second question. Can people see my notebooks as clear as it's, or can I try and do a better job of zooming in?
It looks clear to me. I haven't received any requests in the chat to, to adjust the size or anything. So if that happens, I'll let you know, but looks good.
All right, good. And I'm sorry for not asking those questions earlier, but I think things are going well. And so we're seeing the stars and the galaxy. And so they have some kind of distribution where you see these stars appear to be so these radial velocities with respect to the center of the galaxy, and so some of these stars are moving away from us, and some of these galaxies are moving towards us or into the screen, and can kind of think away from the screen. And so that's pretty cool. But let's change a few things to see how these galaxies change. Okay, instead of doing 77, let's do so just for reference, when a galaxy has an inclination of about 0, that means it's very face on. And so all galaxies are kind of like round, like a plate or a disc or something like that. And so when it's facing exactly towards us, or at least all spiral galaxies are, when it's facing towards us, it's gonna appear circular. So let's try a very small inclination angle to see if that's the case. And so we run that, and then let's try this. Yes, that is indeed the case. The galaxy is in fact face on. And it looks circular as we expected. And then now it's the time where I like the chat to help me out here. What would happen if we plot or we use an inclination angle that's very close to 90 degrees? Let's say 85. I've lost my Zoom here for a second. Sorry.
No worries. Let's see if we get some responses in the chat while you're pulling that back up.
Yeah, that is the reason I'm trying to pull that back up, because I want to see the chat.
So Gavin says it will be very close to a line.
It'll be very close to a line. That is a good answer. Yes, it will be very close to a line, but an even more kind of astronomy terminology will be like it will be edge on. So it would be kind of like looking at a frisbee when it's coming towards you horizontally. So that's a very good answer, Gavin. But let's see. I don't know if it's true. Let's check it out. All right, we're running out with at 85 degrees, and let's see. Oh, yeah. I think it's less of a circle now, and it's more kind of edge on. I think it's better if we kind of let's go close. Can we do 89? Yeah. I think Gavin was spot on. It looks a lot like a line, the closer you get. And I don't want to do 90 because that might break some tan functions. I think tan of 90 is undefined if I'm remembering my ninth grade geometry correctly. But let's put it back to 77, which is the one for M31, and then let's play around with this position angle. What do we think about the position angle? What would happen if we put something like 0.7? It's to give you an idea, just the angle of how it's oriented on the sky. Let's do this. Let's do this one first, and then maybe I'll ask a question on the next one. All right. So it becomes very, very horizontal when you have a position angle that's, close to 0. And so what would happen if we have a position angle close to 90? I think I won't wait for chat for this because I know everybody can guess this now. It would be very horizontal. Okay, so that's just the position angle of the galaxy in the sky. And so you can have more fun with this if you like, and you can just, I don't know, change the inclination again here. And let's make it less, like, I don't know, 30 degrees. So a very horizontal looking face-on galaxy would look something like that, which is pretty cool, I think. We can also now I have forgotten what was the position angle before. I feel like this was the position angle. Yes. Okay. I'm gonna stop there and see if there is any questions.
Checking the chat, I don't see any questions right now, Lordrick.
All right. Let's go on. So, something as I was mentioning earlier, something you want to notice is we can get some information about how the stars are moving, whether or not they're moving towards, and this in this case, it's with respect to the center of the galaxy. But there is another cool thing that we could do is look at the dispersion. Now, as I said, I'll talk a little bit about dispersion earlier, and so the way you think about dispersion is if I pick any star here and define some radius around it and kind of tell what are the stars doing? Are they super different from the way this particular star that I'm interested in is moving, or are they all kind of moving in the same direction or in some in some stream flow? Now you may ask me, why would you even do that? Why would scientists even care about that? That tells us the history about the evolution of the galaxy. So say you have a galaxy that was disrupted, maybe another galaxy kind of went through it. You expect then there is a lot of disturbance inside your galaxy and the stars will be moving every which way. And so that will tell you some information about what's happening within that galaxy. So you'll have a lot of dispersion, a lot of disturbances, essentially in every in variable parts of this particular galaxy. So dispersion in this particular case is just what are the stars in the neighborhood, the way I think about it. What are the stars in some defined radius from one particular stars? What are they doing and how are they moving? That is a very important thing to kind of figure out. And so how are we gonna do it? As I say, we pick a star, define some define some radius, and then kind of average out the differences between the way that particular star is moving to that other stars. But first, before we define any radius, we need to know because these numbers here are in kiloparsecs. From what we observe things in arc seconds and degrees, and so we need something to convert arc seconds to kiloparsecs. And so in your notebook, if you're following along, you won't have this cell because I made this cell in the morning. But I was looking at this in the morning and I was kind of trying to figure out, where it came from. And so this is where it came from. Just start from your normal formula. The arc length is just given by d times theta. And then if Andromeda, and distance is, by the way, is the how far your particular galaxy is, and so if you multiply that by 1 degree to get exactly how many kiloparsecs is 1 degree, you get about 13.67 kiloparsecs. If you don't believe me, I did this in this cell here, and yeah, that is indeed the truth. All right, and so we have now kind of a conversion factor from arc seconds to kiloparsecs. We're going to build two new arrays, which will be the same length as the number of stars that we have. In this case, we have 10,000 stars. And so, building arrays is easy. We just make them full of zeros. We have this smoothing cycle. So essentially what we're doing when we're calculating the averages in some particular radius is like smoothing that whatever parameter you're thinking about. In this case, we're thinking about radial velocity, smoothing that over the entire region that you define. So that's why this variable here is called the smoothing cycle. And in this particular case, we're going to be doing it over 200 kiloparsecs. And so we have 200 kiloparsecs here. 200 arc seconds here, converted to kiloparsecs. And so we have a function defined inside the fake disk object. So you can read about that function here inside this inside this file, but it's not, the details of it are not super important right now. But we're essentially gonna do that for all the stars, and we're gonna calculate the velocity dispersion. And now in our show map, we're still passing our same fake disk object, and then we're passing this sigma value that we just calculated. This is the array. And then we're passing the velocity dispersion just as the label to label our axis. And yeah, this looks good. Yes, Vmin is 0, and then Vmax is 30% more than the maximum value of sigma that is in there. So let's do that. Cool. We see a bunch of patches here where your bluer patches means you have very little velocity dispersion, and your kind of yellower patches means you have more. And so there is kind of stuff happening somewhere in some of these patches. But we only have 10,000 stars. Now, if you know about galaxies, you know that the galaxies have much more stars than 10,000 stars. In fact, if a galaxy has only 10,000 stars, I don't think it can be called a galaxy. I'm not sure.
I was going to ask, yes, because like there are some globular clusters that have more stars than that.
Yeah, exactly, yeah. So we need more stars. Depending on how strong your computer is, you can try and do more stars here. In our case, let's just try and do 50,000. Okay, let's run this again. All right, we have much more filled up here. Hopefully we can see a lot more of that dispersion. And so we don't have to calculate that again, but we do have to calculate this again. This is going to take a second. You should know a lot of programmers' time is spent waiting for code to run. If you ask Maddie, she has code that runs for weeks or something like that, which is interesting. Great that this is not the case for us right now. It would be the case if you do 1 billion stars, for example, probably, I think. But we have now, this is a little bit more clear. You can kind of see the patches here. There's one very distinct one at the center. Here, I don't know, I'm not 100% sure why what is happening with them, but it could be saying something about what is happening in the center here. And there is a lot more patches of those kind of dispersions. I'm seeing a comment in the chat.
Okay. Yes, Aparajito
okay.
yeah,
That
he
was just
added some extra details about while we were seeing it edge on and actually what happens in reality versus what they're seeing here.
Yes, thank you, Aparajito, for that. Yes, indeed, yeah, real galaxies are not super well behaved. Let me just use that terminology. But in our fake simulation here, and so the point of this notebook is just to show that we can, and we do indeed do a lot of simulations in just our whenever, for example, we're looking at stars in a galaxy, we can try and do simulations and simulate stars and all things and do all the calculations that we need, or for example, do an analysis of velocity dispersion in this particular case, just to study our galaxies. And the cool simulations that I didn't get to show, probably someone will show at some point, are usually informed by just quick analysis like these ones. And so to see this better, let's try and zoom in. Remember, I mentioned a cutout argument in our show map function in the beginning. And then let's try and run it and see if we can zoom in towards the center. Very cool. Okay, yeah, and now we are seeing, oh dear, I think. Oh, okay, I see why. We have indeed zoomed in, but you can see this pattern here is not the same as what we have here. That's because I haven't defined the proper parameters inside our show map. Let me see if let me do this. All right. I think this will be better. What am I doing? Let's copy this. Just paste it there. So I want the same zoom in map, but I want to zoom in the velocity dispersion part. And so I'll just copy this. I should also, I keep dropping in these things about programming, which is a lot of programming is copy and paste. More than you would think, actually. All right, that looks good. Let's try that. Okay. The reason it did not zoom in is because I haven't added my cutout. And let's make cutout is equal to true. All right, very cool. Now we have zoomed in. We can kind of see the dispersion kind of defined within this 200 arc seconds region. Still a little bit hard to see, but you can kind of see those patches here. I think one thing that will make it easy to see is if we increase the velocity. So let's increase the velocity, the rotation velocity. And then let's run this again. And run this again. Ooh, let's take 1 second. Great. By the way, don't worry. Oh, now it's super clear. Oh my God, that's nice. Okay, you can kind of see this structure of a lot of dispersion of like maybe some stars are getting flinged out or interacting with each other or something. But by the way, this is a simulated galaxy, so I'm just making up explanations here. But let's zoom in. Oh, this was just for the velocity. Okay, we can zoom in on the velocity. What I want to zoom in now is this. Oh yeah. Here's the structure that I was looking at earlier, kind of this X structure. I think this is just a fact of how this fake galaxy is defined. And so you can kind of, coming from theory, kind of define your simulations to kind of see the effect that you expect. And usually we're trying to match this with observations to study more about these galaxies. Cool, and that is it mostly, but this is kind of left there as kind of something you can work through when you're comfortable with understanding the codes and simulating these galaxies. And so now that you're kind of familiar with the parameters and the figures of effects, try to answer the following questions. Feel free to double click this cell and type your answers below. So let's say you simulated 2 galaxies, and if the 2 galaxies of the same geometry, but galaxy A has twice the rotation speed, and the velocity fields differ on the major axis and the minor axis in between. Oh, how do the velocity fields differ? I think you can see the dispersion here. You'll have more dispersion with higher velocities. So if you have twice, you'll have more dispersion essentially. And then there's other questions here which do we have to go through this? Jamaica, I don't know, I've never done this notebook before.
No, we don't need to go through this. This is actually something they can do on their own, or even with their mentors for their project if they're wanting to get some extra practice, Lordrick.
All
Thank you
right. Yeah,
so
I
much.
will kind of end there, I think 15 minutes before time, but yeah, thank you. And I'm happy to take any questions for which I can answer.
Wonderful. Let me just thank you again, Lordrick. I will say that the simulations that we were looking for earlier, Sergio and Aparajito added those links in the chat, and one in particular, the STSCI interacting galaxy simulations were added there. So that's perfect. And this is will be included, of course, in the chat transcripts for everyone to check out on their own. Now, let me just put the schedule up here. Okay, so next up, we are running a bit early, so this is great. Next, we have Aaron Figura scheduled to start at actually 3:05 p.m. But since we are a bit early, how about we take maybe a 3-minute pause and let Aaron get set up? Aaron, does that sound good to you?
That sounds just fine.
All right, perfect. Okay, so a quick 3-minute break and we'll start at 2:50 Pacific. Thank you so much, everyone.
Jamaica, we can play the Galaxy Collision video in the meantime.
Sure can, sure can.
Okay.
In fact, do you want to do that, Paradito?
Um,
me find it.
Yeah,
I'm trying to
sure.
find it.
I'll
I'm
do
trying to
that.
find it. Okay, if you
Yeah,
have
yeah,
it, I lost it someplace.
yeah. I'll do it.
And in fact, this simulation is so it really shows things very well. Where is it? Oh gosh, I have lost that link. There, this is it. Yeah, here it is. Let me go through it. I found it a part of detail. I'll show it here. Let me put it back in the chat. Let me pull it up. Okay, and let me bring it back and make it full screen. All right, I'll share that now while Aaron is preparing. Thank you. Great suggestion, Aparjito. Here we go. So this link is in the chat. This is actually from the Space Telescope Science Institute. Simulations versus observations. And anyone, Sergio, Aaron Aparjito, Madeline, feel free to chime in on what we're seeing.
So what you're seeing here are two spiral galaxies, and they are rotating, right? So these are simulations, as you can see, like a very complex version of the model you just saw. And what this is simulating is basically the future of our galaxy, the Milky Way, and the galaxy that we're studying here, M31, or Andromeda. Since Andromeda is blue shifted with respect to our galaxy, it means that our galaxies will eventually keep approaching each other until they collide, right? Until they eventually collide. And what this video shows, what this video does is simply take snapshots of that simulation, of that whole timeline of the simulation. It pauses it, and as you can see, it compares it to real images, right? These are real images of real galaxy collisions. We know that this is a phenomenon that happens all over the universe. It has been happening for a very long time. And comparing with real observations is something that theoretical astronomers do all the time. So all of these complex computer simulations, they generate these predictions. And as you can see, we take observations from observational astronomers and we match those results with what we see from the simulations. So this is just a perfect example of that. Looking at the fate of other galaxies gives us insight into the eventual fate of our galaxy. Yeah, that's pretty much it.
Thank you so much, Aparjito. Thank you. Thank you. And also, Sergio put in some fantastic links as well. Please do check those out. Okay, it looks like Aaron is ready with our final notebook. Wow, notebook 6. Let me just again say that if you have any questions, please post them in the chat because everything is being recorded. The chat is being recorded, so your questions could be helpful to someone else who may have that question or hadn't thought about it. So please do. And again, I do want to acknowledge that we had Madeline Broom join us, and I've updated our graphic here to show Madeline as one of our subject matter experts. All right, thank you so much, everyone, and we're ready for Notebook 6. Aaron, take it away.
All right, thank you, Jamika. It's been a pleasure listening in on these and getting to see the different styles, in fact, of the different presenters. And I'm really happy to be here to wrap this up. My name is Aaron. I have been a radio astronomer, an active researcher for 20 years or so. My area of interest is in massive star formation. So we're looking at those really tight large molecular clouds. We get these condensations of dust, and under the right conditions, we want to find out how exactly what the conditions are that cause those to collapse, to form that new breed of the new generation of massive stars. And one of the things we do is whether we're looking at small areas where we might map over a one molecular cloud, or whether we are doing a large survey, is we need to do a strong statistical analysis. That becomes the basis of everything that our research is focused on. Everything that we can build our case on to understand the universe around us is based on that statistical research. This module is going to focus a little bit on that and on some of the tools available. We're familiar now, hopefully, or at least getting familiar with this basic suite of tools that we've been using with Python. We've been using NumPy for handling large data sets, large arrays or matrices. We've been using Matplotlib for our plotting utilities. So what I want to do is just introduce a little bit, use those to do some statistical analysis to help, and visualization of that statistical analysis to help us in our research. So I wanted to let me share here. And I want, oops, I've got to make sure I've got the right one.
No worries, no worries.
All right, let's try this.
Gotcha.
All right, you see me there? You see my desktop? Okay, so there's our module 6, and we're going to come back to that in just a moment. I want to, before I do that, I want to take a look at a couple of examples. And this is just one that I pulled up really quickly from the Matplotlib page. I'm going to encourage everyone, if you're not familiar with it, matplotlib.org is going to have information, examples on all of the routines, all of the functions, all of the classes, everything you can do. And it's a fabulous place to start when you're looking for help in putting together your analysis programs. Now, this little plot here is some nameless plot, and I want to, we could think of this any way we want. Maybe we might look at this, and from an astronomical perspective, we might think it's a globular cluster. And you can look at that picture. Let's say it is a globular cluster. We can look at that picture and we can say, oh, well, we can see certain things about this. We have the heaviest concentration of stars toward the middle of this cluster here. We have, and that concentration peters out as you get further away. So we see fewer and fewer stars, maybe a few that are really far away. And that's certainly an important way to look at that cluster, just to look at it and see what it is. But we can use statistical tools to start thinking a little bit more deeply about that and to quantify some of the characteristics we see. So in this example, we see these two side plots. And these side plots are histograms of the data. What they are doing, what each one of these plots is doing, is you can see that we've separated our x-axis into these discrete chunks, these discrete bins. And what we can do here is you can imagine a column stretching all the way across this image. And all we're going to do from there is we're going to count up how many objects are in that column. So right here, you can imagine this column that runs just around negative 3.7 or 3.8. And we've got two objects, two stars sitting in there. And so we're going to plot that on our histogram plot. There's a little bar sitting right at 2. We've got our little bar plot right there showing that's a value of 2. And we might come over here to this column right next to it, and there's nothing in that one, and that's a 0. And there's another 2, and so on and so forth. And you can see how, as we get toward the middle, the numbers have to end up being very, very large. What this plot then does is it shows us the frequency of events per bin and shows us how those are distributed. So even if we could not see this scatter here, we can look at this and see we've got this collection of objects, stars, and they are most densely located toward the center. That's where the highest numbers of these things are concentrated. And that number kind of peters out slowly, and it has this long tail where we might see these outliers. We might see these things sitting further and further away. And that tells us something a lot more concrete about this object. And you can see here we've got one along one axis, we've got a histogram for the other axis. The two of these, even if that was all I had, even if that was all the information I had, those two histograms give me a lot of information to mentally reconstruct roughly what this looks like. But it also allows me to do some more things with it, and I want to talk about here. We can think about the mean or the median of this distribution. We can think about the peak, how many values does each bin have? And we can think about the breadth. You can imagine if we took all these stars and maybe we compressed them into a tighter space, a big galactic bulldozer that would just squeeze all of these into a much smaller space. You can imagine what might happen to that histogram. We're not going to see these guys out here. We're going to push them all to the center. And when you push those all to the center, that's also going to have the effect of raising this up. So the breadth of this histogram is an important characteristic. Now, you may look at this, you may recognize, hey, I know what that basic shape is. If we wanted to draw a smooth curve through this, we might imagine drawing something that looks very much like a bell curve or a normal distribution. And so we can use the bell curve, while that's undoubtedly not exactly a normal distribution, we can use that as a model. And so we can talk about a standard deviation to describe the width and the mean, and well, we can use a mean and a median anytime, but we can use a standard deviation as a way to describe that breadth. I'm going to pull up another example here really quickly. And this one is an astronomical example. This is from one of the papers that I was on. And we are looking at molecular emissions in some of these star-forming clouds and a number of different molecules. But we have two different ways here of representing some data. And on this lower plot in the blue and red here, we see lots of dots. And this is a plot of molecular rotation temperature versus dust temperature. And we can see some basic trend relationships here. And that's very useful. But it's also really useful to take this and turn it into a histogram. So we're going to draw our bins. And we're going to count up how many objects had a C3, C2H temperature that looked like this, or that fell between this value and this value, or this value and this value. And we're going to do that, and we can show how these temperatures compare between these two different molecules and the dust temperature in this cloud. And that's hopefully going to give us some insight into the behavior of this cloud and maybe star formation a little more generally. So that's sort of our goal here, is to be able to do this kind of statistical analysis. So that's what, let's come back over here to our module, and we're going to go through this and see how we can use NumPy and Matplotlib to this end.
Aaron, could you zoom in your screen just a little bit?
Oh, yeah, absolutely. let me see.
Thank you.
Oh, I don't know if I can remember how to zoom in on the HTML.
I think it's just Control plus and minus.
Oh, yes, Control plus. Control
Control
plus.
plus. Really?
Or
Maybe on Mac, it's
Control
a
and
function plus.
Oh, you did it.
right.
It always gets me. I'm still, I've been working
Yeah.
with this Mac for 5 years and I still forget. All right. So we're here, we're going to look at some of the data we've already been taking a look at that you're already a little familiar with. These sets of main sequence data, red giant branch data, and asymptotic giant branch data. And ideally, we're going to use those to give us some insight into the behavior, the history, the life of the Andromeda Galaxy, at least at some level here. So we're going to start with our preamble here, our imports. You're familiar with those already. And our first function here is show map. Now I want to take a moment just to put in a little bit of a plug actually. And I'm going off script here just a little bit. One of the really fabulous things about Python is the ability to compartmentalize our code. When I first started out, I remember very vividly being told that I code like an astronomer, which was to say it would work, but it was ugly. And as I have evolved as a programmer, I have come to realize how important it is to have code that is simple and readable. Even when you're doing really complicated things and code that's thousands of lines long, you want the individual pieces to be nice and understandable by somebody who's not you, because you may not be the only person who ever looks at that code. So we're going to split things out. We've got this nice little function here called show map. And show map is very simply going to make a plot of a data set. We're going to feed it two arrays of coordinates. We are going to supply labels, and we're going to save that as a file name, with our file name here. So all of these are non-optional parameters. So as we go through this, we can see what this is going to do. We are going to set up our axes using the matplotlib pyplot module. We're going to set our axis labels, X and Y, and set our title. And then we are going to use the matplotlib scatter function to generate that scatter plot. So we've got, let's see if I recall correctly here. So this is basically, we've got 3 arrays that we're passing here. We have, all of these are the same length. We have our 2 spatial coordinates, and then we have the velocity dispersion as quantity that we are passing to these data points. If we do not pass that quantity, of course, we're going to get just a simple monochromatic scatter plot at these points specified by key and eta. And we're going to specify a velocity range to go with that. We'll set limits, create a color bar, save the figure. And we'll see what that does here in just a moment. Now, in order to plot this, we need to generate that quantity. We need to generate the data that's going to go here. And that's where things start to get more exciting. So our function getDispersion is, again, a plot, is going to take us those coordinates and velocity values in order to figure out what the dispersion is. So what we're going to do with this, we're looking at, so if you think back to the example I showed you at the start with the fake globular cluster, we thought about having these little bins where we were going to divide the whole breadth of this cluster up into these little sections, these little components, these bins. That's the term we most usually use. So here we might have negative 3.8 to negative 3.6 and negative 3.6 to 3.4. And we're just going to add everything up in those bins. What we want to do here is very similar, but instead of adding up everything in spatial bins across the breadth of that collection, instead what we're going to do is we are going to add up all of the objects that are close to each object. So we've got this collection of stars in Andromeda, and we're going to look at each star and we're going to look at its closest neighbors. And its closest neighbors are going to become a little bin there. That's the neighborhood that it's going to be looking at. So our last parameter here, circle size, is the size in arc seconds of the neighborhood for each star that we want to look at. We want to look around each star and figure out what the spread of velocities is around that star. Are all the stars moving at the same relative speed? If so, the net dispersion is very, very narrow. It's very small, and we'd see something that looks like a spike function. Are the stars all moving at widely disparate speeds with a high variation? Then we're going to see that very large dispersion. And clearly, how we choose that circle size is going to be fundamental to our understanding. If that circle size is too small, there might be only one object in there. The object, the star itself. And so that small, if you look at the dispersion for one object, it's undefined. So that's not helpful. If that circle size is too large, you're looking over a very, very big portion of the galaxy, or perhaps even the galaxy as a whole. And that's not going to tell you something either. So we're going to have to play around with that, and we'll take a look and see what those what kind of changes that varying that does. All right. So first thing we're going to do, we're going to have we're going to set up a blank array or an array of zeros for each of the same length as our data array. So we're going to pit all of these values, x, z, and v, they all have the same number of elements, the same as the number of stars that we've measured in our data set. And we are going to create our empty array of that same size. And then we're just going to iterate through that list. We're going to run through all of the objects in this data set. And each time we go through this loop, we are going to pick out the coordinates of our particular object, the x and z of that particular object. And we're going to save that here as this x and this z. So as we're going through this, each time we go through it, we're going to focus on a different star. And then we're going to look at the neighbors to that star. All right, so how do we calculate the distance to this star? So this star's distance to itself, of course, is 0. So we want to calculate the distance between each of the stars in this array to this star. So what we might do, we certainly know that we might be able to start by saying distance should look something like the square root of the square of the legs of the triangle, right? So we might say something like the square root of the position of one of those stars, position X. Actually, I don't want to use, I do want to use X. Position X and this particular star's position. So that's going to be the distance in X between those things. Let's square that. And we need to add to it the other leg of our distance triangle. So we'll do the same thing for Z. All right, so this is just the same square root of a squared plus b squared function here. And because NumPy allows you to deal with these arrays so easily, we can throw that whole array in here. It'll subtract this x off from that. It'll subtract this z off from that. It'll square each of them, add them, and take the square root. NumPy makes things really that easy. Now, we don't want to figure out the dispersion to all of these stars. We only want the near neighbors. So what we can do, what NumPy lets us do, we have this thing. This dist is an array. It's an array that is the length of the number of all the other stars. So what we're going to do is we're going to take that and we're going to select certain ones out. We can take that array dist, and if we select only the distances that are smaller than our neighborhood, our circle size, we will get an array, a Boolean array, that tells us whether or not this condition is valid or not. So if the first star is close and its distance is smaller, then keep for that star will have a true. If it's further away and this condition is false, keep will be that particular value for keep will be false. So keep is this Boolean array of trues and falses that tell us whether each of these stars satisfies this condition. So we might even think here of adding a line, and I'm going to do this for just for sanity's sake. And I'm going to call it neighborhood. And this is an array of all the stars that are in that neighborhood. So let's we want to do this for the velocity. So I'm just going to say v, and we know that if I put a 0 in here, I'll get the 0th element of that velocity array, or if I get a 2 or a 3 or whatever. If I put that Boolean array in here, the neighborhood just becomes this abbreviated list. It's a subset of V, but it's a subset of V where the objects are all closer than that circle size. When we do our dispersion, that becomes really nice with NumPy. We're going to use a standard deviation function, and then we can just say, take the standard deviation of that neighborhood array, that array of velocities that are close by. And that will give us our dispersion for that element, for that ith star. So then we can return that dispersion, that array that tells us what the velocity dispersion is for each of the, in the neighborhood of each of those stars. All right. We have questions so far. Is everybody happy and following along?
Yes.
Am I going? Okay.
everyone's following along, and Aparjito is adding in some details as well, adding on to what you're saying here. So I think we're good for now, Aaron.
Absolutely. And one of the things I will mention here is that as you progress as Python coders, you could look at this, and if some of you are more familiar, you might look at this and say, there's a lot easier ways of doing this and making this in smaller amounts of code or simplifying this, and that's absolutely true. And the point here is not to make the most efficient and elegant set of code. We're trying to make easily understandable code. And so as you progress, and I encourage you to keep progressing and learning and seeing some of the techniques as you work on some of these problems, you will see all kinds of different approaches to doing similar things. And so it's always really important to take those, look at those, and learn from them. And the comment there, I have to strongly encourage: comment, make comments. We see lots of good comments here. Hey, this is what this line is doing. This is what this line is doing. I know that a lot of programmers that I have worked with who are not professional programmers get into the mindset that I'm the one that's going to be maintaining this code. I know what I'm doing. I don't need to comment anything. That's obvious. And that sounds really good when you're sitting there working on the code for 8 hours a day for 10 days straight or whatever. But when you decide to come back to that code in 4 years because you moved on to something else, and you came back and you started doing some research that could use this particular chunk of code, because of course you're going to reuse your code. You're going to come back to that and you're going to look at it, and you will really be making yourself crazy trying to figure out what the heck you were thinking 5 years ago or whatever when you wrote that code in the first place. I have been there. So comment your code. It can seem silly. It can seem a waste of time. It is crazy important. All right. So we've got our functions here. We've got our map. We have got our dispersion calculation. So now we actually can sit down and try running this. So let's take we're going to take this, and I think we are all set. Yeah, all right. So we're going to start out by reading in our data. We've seen this function before. And we're going to select out a certain amount of things. So this keep is going to be the same thing it was up here. We are going to get a Boolean array. And what we want to do is we want to select out only certain values. This comes about because of some outliers in the code that will make a mess of things if we include those. So we are going to strip out anything that has an absolute velocity greater than or equal to 1,000 meters per second. So absolute velocity, absolute value of the velocity, and again, that same formulation, that same logical formulation, and that will give us this Boolean array. And then we're just going to take our three data arrays here, our two position and our velocity. We're going to redefine them. Now, normally, I'm a little bit wary of redefining parameters like this, because this key is not the same as the key we read in up here. But here we're throwing away this, what amounts to bad data for us, and we're just going to hold on to the good data. And so that's a fairly typical thing you'll see done. All right, we've got our two functions. We're going to get the dispersion, and then we're going to plot a map. Let's see how that works. All right, so now we see our velocity dispersion. Now, we've seen the same basic data before. We have a dot at each position for each of the stars in our data set. But now what we're plotting is something different. We're not plotting the radial velocity, we're plotting velocity dispersion. So at each point, we're looking at or what that standard deviation of velocities is around our star. And you can see that we've got a couple of areas where we've got a little bit of a higher dispersion, but overall we've got a whole lot of very low dispersion stars. So velocities of all the stars in the neighborhood are pretty similar, is what that's telling us. So around each of these stars, we're seeing that the radial motion is fairly uniform. And what we want to do with this is play around just a little bit. So remember that our dispersion, that our get dispersion function takes this parameter of circle size. I'm just going to copy this. And I'm going to bring this down over here. And of course, as this circle size is a non-required parameter. We can specify that, and if we don't specify it, it will take on this value. So what I'm going to do is I'm going to throw it in here, and I am going to start playing with it. So if we take this and we make this larger, so I'm going to double the size of our neighborhood. And you can sit and think for yourself, what happens? Well, if I am calculating the velocities of an area that's larger, I should see a broader range of velocities, so I should see a higher overall dispersion. So I'm going to double the size of that and run it. And that hasn't changed an awful lot here. But we do see much more greens down here, where we just saw a couple of knots before. Now this is looking a lot more green. Let's crank it up again. Whoops. And we're seeing a lot more uniformity now, as everything in the region now is taking on the same, each of the stars here are seeing the same dispersion because they're essentially measuring the same neighborhood. And what's kind of interesting is that we see that vary a little bit from one end of this to the other. But we can play around with these numbers and think a little bit about what it tells us each time. As I go to a smaller circle, now we're seeing a lot more variation because we're not averaging over the same neighborhoods. All right. So now what would be nice to see is, having done this I'm going to return this to our default value for now. And having performed this calculation for our main sequence stars, let's take this and replicate it. So now we're going to change this and look at our asymptotic giant branch stars. So we're going to change our catalog. We are going to change our output file. And we're going to run it. And we're going to wonder, uh-oh. I am not sure what I did. This worked before.
Oh, did you run Notebook 3?
Say again?
Did you remember to run Notebook 3 that creates the catalog files?
I may not have run Notebook
Yeah.
3.
Do you have the completed notebooks? There's a link.
I do.
Yeah.
Just a
Just
second.
copy over the data folder and you should go.
Yep.
I apologize, everyone.
Remember everyone, you have to complete Notebooks 3. If you don't, you won't find the data, but if you run into the same issue, it's fine. It's totally fine. Just check out the recording from the first session and borrow the data files, maybe from your SIP teammates if you are a SIP scholar, or feel free to or feel free to follow along with some paper and pencil for now, so that you can run the notes later.
No, thank you for I actually did not remind Aaron of that. That was my fault about Notebook 3.
By the way, Aaron, you can just copy over the data folder from the completed notebooks directory.
Oh, okay. You know what? Gotcha.
Yeah.
That would be easier.
I think that should have worked.
I could have sworn that I had run through this, but apparently
I've run into the exact same issue before. Yeah, it's easy to do.
All right, just give me half. All right, so I'm gonna drop me back right over here and let me go and do that here real quick.
And while Aaron is doing that, please check out the comments in the chat. So one of the points that Aaron made was about the importance of keeping your code simple. And you can read Aparajito's supporting comments for that, as well as Madeline's. It's really important. So make sure you check that out. And also to Aaron's point that also Aparajito made yesterday during the first notebook about commenting when you're going through your code. And Aparajito put some good details here in the chat about the importance of commenting out. So please do that. And let's see. And the other thing too is these kinds of mistakes happen, or you have challenges that occur in programming all of the time. And this is why I'm so excited to see our experts here. When that happens, we get to hear and see them go through this in real time, because even experts sometimes have to go through and make some corrections. Aaron, yeah?
Absolutely. I know I spend more time debugging than I spend programming. I think that's fairly safe to say. And you know what? Before I get right back to this, I'm going to point out one thing, and everybody can cringe at me. All of my fellow presenters here may cringe at me for doing this. But as someone, in my role at Gemini Observatory, one of the things I do is I lead up a group of programmers who are creating code. And we've got some code that is 20-year-old Python. We've got code that was written earlier this week. And so it's really one of the, to stress what's been said before about commenting, about writing, readable code blocks. I'm going to encourage everyone. You don't have to do it right now, but I am going to encourage everyone to to go and take a look at the PEP 8 style guide. Python will let you write very ugly code. Python will let you do all kinds of things that you shouldn't. It'll let you do all kinds of things that are difficult to read. And style guides are there for legibility. They're there to help you be able to read it. They're there to help other people. I have to maintain other people's code, a lot of it. People who no longer work at the observatory, who retired, who passed away. This is one of the things that you can do to help make sure that your code can continue to be used and maintained. And it's going to include things, even including like, where do you put spaces? How do you tab? I will admit this code right here makes me a little bit crazy because we should, good style puts spaces around these equals. Does it make a difference to the execution? No, it doesn't. But it helps keep things uniformly legible. So when you go from one piece of code to the other, you don't have to adapt and figure out what you're looking at. All right, little mini tirade aside, here we've got our AGB data, and I've actually got our data calculated, copied over now. So here we can see our dispersion plot for that. And we can see that this is very, very different. This is our main sequence data. I don't think I reran it at 300. There's our main sequence data. We see that velocity dispersion is very, very low. When we go to our asymptotic giant branch, we have much more variation in velocities. We've got a much stronger dispersion. And let's go ahead and do our red giant branch. And change the catalog. And change the output plot. And now this looks very, very different. We see much higher dispersion for that red giant branch. We can see mostly greens and aqua type colors here. So we put all three of these side by side. We can compare them much more easily. Interestingly enough, Matplotlib has the subplots capability to allow you to make side-by-side plots, horizontally, vertically, or a grid. They're fabulous. All right. So with all that in mind, we want to make some histograms. And histograms are actually really, really easy. Again, between NumPy, between Matplotlib, they do the hard work for us. So let's create some histograms. So I want to create a couple of axes, a plotting space. And in order to create a histogram, I'm going to bring this over from our completed. And I am going to use the Matplotlib histogram function. So this takes a single data argument. So this is a main sequence dispersion that we calculated above. And we're going to specify a little information. How many bins do we want? Obviously, the number of bins you want depends on how much data you have. If you have 20 data points, having 20 bins is not really helpful. If you have many, many data points and you can support finer bins, but you also may want them larger depending on what your data represents. So let's leave it here for 30 for the moment. We'll play around with that. We're going to specify that we want to norm the data. So if we looked at some of these, if I look at some of these plots that I had as an example, we're just doing the number of counts here. And if I want to compare two data sets, one which has a large population, one that has a small, that can make it very difficult to compare these things. What norm does is it normalizes the data so that the integral of data of the values underneath the curve is equal to 1, and that allows us to compare a little bit more easily. So we're going to set that to true. We're going to set up the range. We're going to specify what we call a step-filled type plot, which I'll show you what that looks like in a little bit. We'll give it a little bit of alpha, a little bit of transparency, set the color, and I'm just going to run this, and it's going to complain at me. And I'm going to look through my traceback, and I know what this problem is. My version of Python is apparently a little bit different, and my Python does not accept that normed keyword. So I'm going to remove that and run it again. Now, hopefully your version of Python is up to date. Apparently, I need to go and update mine. I discovered this morning. But here we have our histogram of our main sequence data. Our step filled gave us this sort of uniform appearance here. If we want a little bit of an edge to it, oh, one other thing I'm going to note here, pardon the outside noise. This formulation to the left, histogram is going to return information to us. It's going to return 3 parameters. We don't, for this application, we don't care what that return is. And I could just eliminate that entirely. And if I rerun it, it will dump those returns out here to standard output. I don't want that. So basically this formulation here says there's going to be 3 things there, and we want to throw all of them away. We could also save those if we wanted. One of them or any of them or none of them. That's up to you and your particular use. All right. So what I wanted, the other thing I was going to do here is I was going to take this and I was going to give a little bit of an edge for appearance's sake to our plot. So this is going to be the exact same plot as what we just created, but we are adding to it a different plot type, histogram type. And so now you see we've outlined that data and give it a little more, it makes it look better. And aesthetics are good. We also don't have any kind of labeling on this. So let's add a label. So this is our main sequence data. We're going to put our text in over here. We're going to color the label blue to match. And then we're going to let's set up label our axes and set some X limits. So now that's looking good. We've got our main sequence label down there. We've got our y-axis, our histogram axis labeled, and we've got our x-axis labeled. So now all we need to do is to take this, if we want to add our other data sets in here, we are just going to replicate that. And again, you might look at this and say, wait a minute, we can do this much easier and faster. We can do this in less lines of code. And you are absolutely right. We can totally do that. What are we doing? This is AGB. And if I was doing this on my own, I would undoubtedly do exactly that. Set up a nice little loop so I am only writing these histogram commands once. But that's not what we're doing here today. Write it out. Take your time until you know what you're doing. And if I have gotten everything, and I think I have, now when I execute did I not return AGB sigma? Oh, I did not. And yes, this is a lot how I program. Try it out, find out it didn't work. Oh, we need to repeat the whole thing.
I think this is also a great, again, a great reminder for our students to see that this happens.
This happens.
Gonna breathe in, retrace your steps, and go at it again.
Absolutely. All right. AGB. All right, I think good. Yeah, go ahead.
I was just going to say, while Aaron is finishing that up, Aparajito added in the chat how just a point of reminder how important this library is, Matplotlib. It's a very powerful library, and of course there are other plotting libraries in Python, but most of them, as Parajito is saying here, use Matplotlib as a dependency. So it is very important to, maybe when you have time, to really explore all the things that it can do.
Absolutely. Matplotlib is extremely powerful, and there are a bunch of other really cool tools out there. But just as you say, they are in many cases using Matplotlib underneath. And understanding Matplotlib will definitely go a long way to understanding what other things are doing. All right, let's try this again. I think we finally got to the point here. Remember that I was not able to norm my data, that my histogram function did not include that as a possibility. We could code that in manually here and take a few minutes to do that, but I think we'll leave that as an excuse, as a exercise for the viewer. What I am going to do is come over here, and I want to change the position of some of my text. I did a straight copy over, and all of my text ended up on top of itself, and apparently it still did. Did I not move it enough? I did not. Oh, right, because it's normalized. One of the things you'll also find out is that many of the functions that are placing lines or placing text on a Matplotlib screen can be configured to either do it in terms of screen coordinates, so from 0 to 1, or in terms of data coordinates. So let's see if I remembered which one it was using. And there we go, I did. So here we see our three different data sets, our very low dispersion main sequence stars. They're sitting in the disk. They are surrounded by lots of other stars that are all going roughly the same velocity that they are. But as we look at red giant branch and asymptotic giant branch, we get a different distributions of velocities. We see that the dispersion tends to be higher for both of those, much higher for the red giant branch. One of the interesting things here is to take a look at the standard deviation. If we look at how broad these distributions are, the red giant actually is moderately narrow. The asymptotic giant branch is much wider. Does that tell us something about those stellar populations? Absolutely. All right. And the last thing I want to do here is to simply report what those values are. And in fact, what we could do is we could take this and include that onto our plot and actually make that information part of our label. And I'm going to put our other two over here. And this is, whoops, didn't need that one. So we're going to do our print function. We're going to print it out to one decimal place. And we're just going to calculate. Here we are calculating the median of each of those data sets in line. And if we look at this and match it up, there's our main sequence, about 60.4 for the median. Now, that's off to the side of this peak, but remember that main sequence distribution actually has this extra peak over here we see in this data. And we look, and we can compare the other two, the asymptotic giant branch in green, about 92 for that center, the red giant branch at 105. So these tools, which is, what we've shown here today, is just a little smattering, a little sample of the mathematical tools and plotting tools that you have available to you in Matplotlib and NumPy. There's an awful lot more. We can do, one of the things that I will commonly do with data like this, if I was looking at these populations, I would want to take a look and say, let's do a test. Do we have evidence that that this green sample and this red sample are drawn from different populations? So, I might use a Kolmogorov-Smirnov test on that to give me a likelihood that those are two different populations of the same population. Because looking at it by eye is not enough. And certainly making the argument one of these is red on the plot and one of these is green on the plot will not help get you past the manuscript reviewers. So, but there are all those tools that are available that make it very easy for you. And I think that's really where the strength of Python, or one of the major strengths of Python. So many people use it, and not just use it, but use it for scientific data analysis, that somebody's probably come up with the basic tool that you need to do your tests, to do your plotting. You just need to adapt it to your own particular situation. All right, and I think that wraps me up.
Fantastic. Thank you so much, Aaron. Woo! What a great way for us to finish up. All right, wonderful. And to follow up all of these wonderful notebooks, we have Madeline Broom, who'd like to share just some quick insights with us. Madeline. And let me find your comment here.
Hi, everyone. So I imagine a lot of you, especially if you're still in high school right now, and you're probably a lot better at some of the tools of the future than some of us old fuddy-duddies are, thinking, why do I need to learn any of this when I could just vibe code it all? And LLMs are definitely powerful coding tools. I now use them almost weekly in my research to generate code for numerical methods that I'm familiar with. And that's what actually makes me qualified to tell you how frequently they are still wrong. So there may come a day when we can just vibe code everything, notwithstanding, the ethical arguments about AI use. But until these LLMs are perfect, you need to have a strong enough grasp on the fundamentals. Think of it like learning how to spell or learning grammar, in order to sanity check both the science and the code that they are returning and to identify errors. Because if you don't, and you generate something with AI during your SIP project and you kind of just trust it blindly without carefully checking the code, you might actually be fine for your SIP project. But some seriously wrong data or even wrong scientific conclusions could end up in publications that are based on the work that you're doing during SIP, because one of the really cool things about SIP is that you're doing real science here that people are going to build on in the future. So that's my disclaimer. I know you guys are learning a new tool and it can be really powerful to use tools like ChatGPT to check. But if you are going to use it to generate code, use the things you've learned here today to go back and look through and sanity check it. Make sure it's actually doing what it says it's doing, what it looks like it's doing, even if it looks like it's returning the right answer. Trust me, I've had things return that look like correct answers to me, and I go back and I look at the code and I say, oh, nope, you're doing the science all wrong here. So that's just my disclaimer.
And it's wonderful. Thank you so much for sharing that. Absolutely, absolutely. And I think we all needed to hear that. So I'm glad that you shared it. And I also put that word for word in the chat that she shared so that it is captured in the chat transcript for everyone. Okay, now as we wrap up, and we are right on time here, please, I'd like you to all thank our subject matter experts and mentors for all of their amazing help and guidance during these tutorials. Yes, yes, thank you. That is Aparajito, Madeline, Aaron, Sergio, Annalise, and Lordrick. I also want to thank each of you for being here and for taking the time to go through these notebooks, whether you installed Anaconda and were doing this live with us or taking notes and you're going to go back and work through these notebooks at your own pace through the recordings. This is a worthwhile investment of your time.